Hello, everyone. Welcome to Chapter 3. And this week we're going to be talking a little bit about image formation and radiographic quality. So, this is basically where we're going to start connecting everything that we learned last week in Chapter 2 to what is actually going to show up on your X-ray image for your patient. So we're going to start off with basically the term image formation, or not necessarily the term image formation, but why do we see what we see on our X-ray image? So we somewhat define image formation, or the book defines image formation as a result of differential absorption of the primary X-ray beam as that beam or those X-rays are interacting with the patient's body. So as that X-ray beam passes through the patient's body, is going to interact with different tissues or different types of tissues differently. So depending on what it's actually passing through, some of it gets absorbed inside of different parts, and some of it actually makes it through. So that's basically the different body parts are absorbing the X-ray beam differently. So body tissues that absorb the X-ray beam more readily are going to be things like bone because they're more dense, and body tissues that allow the beam to go through more easily are going to be things like our air-filled lungs. Now, with that being said, in your readings, you might hear something about atomic number, thickness and density of those body parts. That's also going to play an effect. Tissues that have a higher atomic number, like bone, will more readily absorb the X-ray beam, and tissues that have a lower atomic number, such as, air, is going to more readily allow the X-ray beam to go through. So again, those that absorb, they will create white areas or lighter areas or shades on our X-ray beam, and those that allow them to go through, let's say you're looking at a chest X-ray, those that allow the beam to readily go through are going to create the darker densities, like the dark shades of gray and also the black on your images. So just kind of a brief thing to remember about this. Atomic number is basically the number of protons in the atom of a nucleus. So bone has a higher atomic number. Air-filled organs have a lower atomic number. So bone is going to absorb a lot more of the X-ray than the other body tissues, such as muscle, fat, soft tissue, or our air-filled lungs. And that does make a difference on what we see in terms of the image. So visually, I want you to think about looking at a chest X-ray, or you can pull up a chest X-ray so you don't have to visually think about it in your mind. So when you're looking at the chest X-ray, you'll notice in the center we have the spine, even though that's not what we're looking for in terms of imaging a chest, but in the center you have the spine. You also have the rib cage, and then behind the rib cage or within the image, you see a lot of very dark or black areas. All right, the air within the lungs allows the X-rays to penetrate through easily. That's why you see the darker shades. All right, dark means that the X-ray beam got through unimpeded and it was actually able to interact with our image receptor. The other white areas that you see, the ribs, and also the spine, they are composed of a higher atomic number. So they're thicker, more denser, and they attenuate more of the X-ray beam. So that's why they appear lighter, brighter, or even whiter on the X-ray image. So here's a visual of what differential absorption actually looks like. So if you remember on the last slide, it said that basically it's composed of the fact that some of the X-ray photons are being absorbed, and also some of the X-ray photons will be scattered with every image. So Here, the high density bone will attenuate more of the X-ray photons, meaning they won't allow it to pass through. As a result, it's going to create the light or white areas on our film. And in other areas, like air-filled lungs, it will attenuate less of the X-ray beam, and it will allow it to get through and actually reach the image receptor. And those that reach the image receptor are responsible for the darker areas on our X-ray image. So again, attenuation just basically means that we have a reduction in the number of X-ray photons that went in as they actually pass through the patient, less will come out. Now, attenuation is required in order to get an image. If all of the X-ray photons that went into the image were absorbed within the patient and none got out, we don't have an image. If all of the X-ray photons that actually intercept with the patient all got out at the same degree, we don't have an image that's representative of what we need to see. It would all be one shade, one homogeneous shade of gray, black, whatever that shade might be. So if you're looking at this particular image, I'm a visual person in terms of numbers. So let's count the number of X-ray photons that went in. Just visually, there's about 1, 2, 3, 4, 5, 6, 7 X-ray photons that went in. Just a visual number. There's many more X-ray photons, but visually speaking, 7 X-ray photons went in to create this particular exposure of the patient. Now, what actually came out was a whole lot less than 7. So the squiggly lines and arrows that you see coming out, interacting with the image receptor on the back side, there's only 2. So that means that the rest of them were either absorbed within the patient, meaning the X-ray photons were absorbed within the patient, or they were scattered. All right, when I say scattered, that means that they are now off focus and not in line to reach the image receptor in the spot where we want it to reach the image receptor. Scattered photons, which you'll learn a little bit later on, they're not good for imaging, and they're not good for the technologist either if they happen to be in the room, because it not only degrades image quality if we don't collimate it out or use a grid to actually reduce it, but it also affects your dose as a technologist if you happen to be in the room. So again, if you happen to be in the room, your dose can actually increase because of scattered photons. When X-ray photons enter the patient's body, a few different things can happen, but one of the things is that it can be completely absorbed, meaning the X-ray photon that enters can be completely absorbed. So that's what we're talking about right here with the photoelectric effect. The photoelectric effect, with this particular interaction, we have an X-ray photon or photons, they're coming into the patient's body. They are hitting tissue atoms and interacting with inner shell electrons of those tissue atoms. So if we drew out an atom where the innermost shell is the K shell, the X-ray photons have enough energy to knock that electron out, that K shell electron out, and as a result, it gives up all of its energy doing that. So it's going to be completely absorbed. Now, a small or low energy X-ray photon might also be produced as a result of that, but it usually is not going to have enough energy to travel very far. It's typically going to be absorbed within the patient as well. Now, how often does this happen will depend on the energy of the X-ray photon coming in, meaning how strong it was, what you set on your control panel for KVP, and also the atomic number of the tissue, meaning what type of tissue is the X-ray photon interacting with. Is it bone? Is it soft tissue? Is it muscle? Is it air-filled lungs? Some of the body tissues, we already stated, they have the ability to or more readily absorb the X-ray photon, and some more readily transmit the X-ray photon. So the main thing to remember about photoelectric absorption or the photoelectric effect is basically the X-ray photon is completely absorbed. Another thing to remember is this interaction happens with inner shell electrons within the tissue atom. The second thing that can happen when the x-rays enter the patient's body is something called scattering. So the main type of scatter that you as a tech are concerned with is going to be something called Compton scatter. There are other types of scatter which will probably be addressed in another lecture, but we're concerned with the Compton scatter. So with Compton scatter, we have x-ray photons coming into the patient. They're hitting outer shell electrons, middle to outer shell electrons. Remember that photoelectric effect, we're talking about inner shell electrons. With this one, it's mostly middle to outer shell electrons. When it does interact with that electron, it does have enough energy to eject it, but it doesn't give up all of its energy ejecting it. It only gives up some of its energy ejecting it. So with this one, the electron is not completely absorbed. Instead of being absorbed, it is going to change directions and it's going to continue traveling as what we call scatter. Now, Compton can happen at all of the X-ray energies that we see in diagnostic imaging. So it really depends on the energy of that X-ray photon, meaning what you set on your control panel. With this one, we're not concerned about the type of body tissue that it's interacting with. So it happens in bone, it happens in soft tissue, it happens in soft muscle, etc. As the KVP that you set on your control panel increases, the likelihood of Compton scatter also increases. All right, so again, this one only depends on, or only is dependent on the energy of that incoming X-ray photon. Scatter itself is something that we can control as a technologist, and we want to control it as a technologist because it can reduce our image quality. It can contribute to our dose as a technologist, and we ensure that our dose is low if we happen to be in the room, or lower if we happen to be in the room by wearing lead. But as far as image quality is concerned, this is where we use either a grid to clean up scatter, or we collimate to clean up scatter. Again, scatter creates what we call fog on the image, so it detracts from the contrast that we would want to see from the image. Now, just to wrap up the two things that we talked about, were photoelectric effect, and we talked about the Compton effect. Some people call it Compton scatter. Some people call the photoelectric effect photoelectric absorption. So photoelectric means complete absorption of the incoming X-ray photon, and Compton means that the photon loses some of its energy and changes direction as it interacts with the tissue atoms. On this slide, we're looking at a side-by-side visual of what photoelectric effect or photoelectric absorption looks like, and also Compton scatter looks like. So really quick, I'm going to point out before I start talking about both of them, the photoelectric effect, we're concerned with the incoming X-ray photon interacting with an inner shell electron. With the Compton effect, the incoming X-ray photon is interacting with a middle to outer shell electron. As you can see right here, that outer shell electron is ejected, and then the X-ray photon continues on its way, but in a different direction. All right, so any of the shells can be involved here except for the inner shell, because the inner shell interactions are involved in the photoelectric absorption. So on this photoelectric side, we have that X-ray photon coming in. All right, this is your X-ray photon coming in, meaning the X-ray that's coming out of the X-rays that are coming out of the X-ray tubes. This is representative of a tissue atom. All right, so it's coming in and it's interacting with an inner shell electron. It is coming in with enough energy, so the KEV or KVP is high enough to actually eject that inner shell electron. Once it does knock that electron out of its shell, it is giving up all of its energy knocking this electron out of its shell. All right, as you can see right here, it leaves its shell and it exits, leaving a vacancy right there. So again, with the photoelectric effect, the incoming electron or incoming X-ray photon is completely absorbed. Now, when we look at the Compton effect over here, with the Compton effect, and I don't know why it has this one ejected, because it's not ejected. If we're talking about a fresh Compton effect, it wouldn't. But we have an incoming X-ray photon, so that we're talking about Compton scatter. It's coming in and interacting with a middle or outer shell electron. So in this case, we're talking about an outer shell electron. It gives up some of its energy, knocking this electron out of its shell. So as you can see, it ejects it, but it still has enough energy to keep going on. So it knocks the electron out, but it does still have some energy left. And as a result of having that energy left and knocking that out, it changes directions and it can continue traveling as scatter. Now, the scatter photon can travel in any direction, including traveling and interacting with our image receptor. All right, if it does hit our image receptor, then it does have the ability to affect the image quality in terms of the contrast of the image. Scatter produces fog on an image, and just like when we drive in fog, fog makes it difficult to see. In imaging, that's the same thing. It makes it very difficult to see. All right, so this is the difference between the photoelectric effect and the Compton effect, also known as photoelectric absorption or Compton scatter. Now, on the last slide, we gave you the visual for photoelectric absorption and Compton scatter. On this slide, we're going to put it in a nice little box or chart for you to go through and try to memorize and visualize. Maybe you can put your pictures side by side so that you can look to see what's going on. So again, here we're comparing photoelectric to Compton. So we'll start with the photoelectric effect since it's at the top. With the photoelectric effect, we have an X-ray photon coming into the patient. It hits an inner shell electron, so we're talking about the K shell of an atom. It has enough energy to knock that electron out of its orbit or out of its shell. It gives up all of its energy doing that, so that incoming X-ray photon gives up all of its energy doing that, and it is completely absorbed. Now, that is where we stopped on the drawing when we did the visual, but that is not where the process actually starts, and this is what is depicted right here in the chart. When we knock that inner shell electron out, it creates a vacancy in an inner shell of an atom, making the atom unstable. Atoms don't like to be unstable, and they will get back down to their stable state. So as a result of that vacancy, we will then start to see outer shell electrons dropping in to fill the inner shell vacancies. They'll continue dropping into the vacancies until all of the inner shells are filled. All right, as a result of the outer shell electrons dropping in to fill those inner shell vacancies, they do give off or release a small amount of energy when they're doing that. Photoelectric interactions happen a lot more with either lower KVPs, meaning the X-ray photons aren't strong enough to penetrate and get out, and also with tissues that have a higher atomic number. So of all the tissues that we've talked about that you'll be interacting with: bone, soft tissue, muscle, air-filled organs, that's it. Of all of those tissues, bone has a higher atomic number, so bones are more likely to create or increase the photoelectric effect. All right, moving on to the second one, looking at that Compton scatter. With Compton, we have an X-ray photons coming in. It will usually interact with an outer or middle shell electron, not an inner shell electron. It has enough energy to knock it out of its shell, but it's not going to give up all of its energy knocking it out. It's only going to give up some of its energy knocking it out, and then it will change directions and keep moving within the patient's body. Now, the electron that it knocks out is called scattered radiation, and that scattered photon might stay inside of the patient's body, meaning it's not strong enough to exit. If it is strong enough to exit, it might hit the image receptor in a place that we don't want it to if we don't control it via grids or via collimation. Or it might expose someone that might be standing in the room. So that could be you, or it could be the radiologist, or it could be if you have, let's say, a nurse or a family member in there holding a patient, it could be them. Now, if scatter reaches that image receptor, as we said before, it doesn't give us any useful information. It can actually make the image look worse if it's not controlled. It creates what we call fog on the image. And if fog is on the image, it can degrade that image quality. So again, we do want to control scatter by either using a grid if it's warranted, or we want to ensure that we collimate properly. Now, this Compton effect, as we stated before, it does depend on the KVP. Now, as KVP increases, the likelihood of Compton scatter also increases, because now those X-ray photons are strong enough to get into the patient and actually get out of the patient. If they get out of the patient, if they're off, I'll say off focus or off direction, and we haven't collimated, then it can fog our image. Now that you've learned a little bit about what attenuation is, we're going to look at some of the factors that can affect how much attenuation is actually going to happen. So there's 4 things listed here. We have tissue thickness, tissue type, tissue density, and also X-ray beam quality. So pretty simple. The first one, tissue thickness. The thicker the body part, the more X-rays are going to be absorbed or scattered. All right, so more tissue potentially means more attenuation. The next factor is the type of tissue. So different tissues are going to absorb the X-ray beam differently. So the tissues that you'll typically X-ray are going to be bone, soft tissue, muscle, fat, air-filled organs. So of those tissue types, bone, because it has a higher atomic number, it will absorb more of the X-ray photons than an air-filled organ. All right, vice versa, bone will transmit less X-ray photons through to our image receptor than air-filled organs. The next one is tissue density. So tissue density, think about, atoms being tightly packed in. So in terms of tissue density, I'll say what I want you to think about is fat versus muscle. All right, so the denser the tissue, the harder it is for the X-rays to pass through. So denser tissue, like muscle, will attenuate more of the X-ray beam than less dense tissue, like fat. All right, the last factor that's listed on this slide is X-ray beam quality. I want you to think about KVP. When you think about X-ray beam quality, when we increase our KVP, we give our X-ray photons a lot more energy. They're stronger, they're able to penetrate better. So those higher energy X-ray photons can penetrate the body more easily, which means that there would be less attenuation going on. Whereas if we have a lower KVP, it will not be able to penetrate easily, and we will have more attenuation happening. Here's a nice little chart that your book gives you to kind of look at what is all happening in terms of factors that affect attenuation. Across the top, just in terms of definitions, before we look at the 4 factors that we talked about, if you could just remember what attenuation means. That just basically means that we're reducing the X-ray beam as it passes through the patient. With absorption, that means that the X-ray is totally absorbed within the patient's body. And the term transmission, I don't think we talked about it, but that means that the X-ray actually makes it all the way through the patient, and it's going to be able to interact with our image receptor. All right, so we're going to first look at your tissue thickness. All right, and it gives you arrows to what happens if the tissue thickness gets thicker, meaning the body part is thicker, or what happens with thinner body parts. And it tells us what will happen to the X-ray beam as it passes through that tissue in terms of, will it make it less or more in terms of attenuation? Will it be completely absorbed, or will it make it less or more in terms of transmission? So looking at tissue thickness first, if we have a thicker body part, that's what it means by increasing thickness, then beam attenuation will increase, meaning a lot more of the X-rays that go in will be somewhat, I'll say, absorbed, so to speak. Absorption increases, so we can look at attenuation and absorption in that same type category. Now, if it is absorbed, if the X-ray beam is absorbed, that means obviously less will be transmitted, less will get out. So with your thicker parts or thicker patients, their body parts will attenuate more of the beam, they will absorb more of the beam, and they will let less of the beam get out to be able to interact with our image receptor. Vice versa, with our thinner body parts, it will attenuate less of the beam, meaning it will absorb less of the actual X-ray photons in the beam, and it will transmit more, meaning it will let more of the X-ray photons come out and interact with our image receptor. All right, with tissue atomic number, increase in atomic number versus decrease in atomic number. So what I want you to attach with increase in atomic number is the tissue bone. And what I want you to attach with the tissue decreasing atomic number is an air-filled organ. So with bone, it will attenuate or absorb more of the X-ray beam. And if it is attenuating and absorbing more of the X-ray beam, that means that less will come out, less will be transmitted to our X-ray beam. And we know that because those shades of bone will be shades of white, which tells us, or light areas, which tells us that a lot of those X-ray photons in that area were absorbed or attenuated. All right, decrease in atomic number, we said we're looking at air-filled organs. They will attenuate and absorb less of the X-ray beam. And if they're attenuating and absorbing less of the X-ray beam, that means that they are letting more of the X-ray beam out to interact with our image receptor. So in those areas of the air-filled lungs, you can see that those areas are the darker shades of gray or black on the image. All right, the next category is tissue density. What I want you to attach to increasing tissue density is muscle, and I want you to attach fat tissue to, or soft tissue to, decreasing tissue density. So with the muscle tissue, because it's so dense, it will attenuate and absorb more of your X-ray beam. And if it is attenuating and absorbing more of your X-ray beam, that means it is letting less of that X-ray beam out. So less of the X-ray photons will be transmitted to interact with your image receptor. Last but not least, for tissue density, if we're looking at fat and soft tissue, it's less dense, so the X-ray beam will be attenuated less and less will be absorbed. And if less is absorbed and attenuated, that means more of the X-ray photons are able to exit the patient and be transmitted to interact with our image receptor. All right, the last category right there is X-ray beam quality. What I want you to attach or associate with increasing beam quality is high KVP. And what I want you to attach to decreasing beam quality is low KVP. So with higher KVPs, the beam is stronger, therefore it may be attenuated or absorbed less. And if it is attenuated and absorbed less, that means that more is able to penetrate the body part, be transmitted to interact with your image receptor. Now the last thing on the chart is decreasing beam quality, so low KVP. If you're setting a lower KVP, It potentially, depending on the body part, can be attenuated or absorbed more because the beam might not be strong enough to penetrate. It has less power for penetration. And if it is being absorbed or attenuated, that means that less of the X-ray photons will be able to exit or be transmitted to interact with our image receptor for image formation. This slide is trying to give us a visual of what is actually happening to those X-ray photons that actually make it through the patient. Basically, this is where the term exit radiation or remnant radiation comes in. Now, with X-ray production, some of the X-rays pass straight through the patient. There's a definition that you need to look up, or a term that you need to look up, that's transmitted radiation. So transmitted radiation is what's needed to help create the image for us. So basically, what we're looking at in this visual here, some of the X-rays are absorbed in the patient, so they never reach the image receptor. Some of those X-ray photons will scatter and change direction. If they do happen to reach our image receptor, they'll create fog. Fog is not good for our images. It will reduce the image contrast, meaning it will be more foggy or gray and reduce that image quality, making it a little bit more difficult to read or decipher what we're looking for. So that is basically what this slide is trying to give you a visual of. Some of the X-rays will be absorbed, some of them will scatter, and also some of them will be transmitted to help create the image that we need for the patient's diagnosis. So really what this is terms. You need to know what remnant or exit radiation is. You need to know what absorption and attenuation entails, and you need to know what scatter entails, what scatter radiation is, why it's bad for your image, and also what we can do to, I'll say, control scatter. Now, the slide doesn't talk about what we can do to control scatter, but you need to do some research on what we need to do in order to control scatter. All right, so now with this image, we want you to kind of try to visually connect what we've talked about in the previous slides to what you're actually seeing on the X-ray. So remember, some of the X-rays must be absorbed or will be absorbed by the patient. Some will pass through and reach the image receptor. Some will scatter, but we're not really talking about the scatter on this particular image that we're looking at. Now, if more of the X-rays are absorbed, like they are in bone, that means that fewer of those X-rays are reaching the image receptor. So that on the image, that will appear as those brighter or wider areas on the image, such as bone. All right, bone here, bone here. All right, if more of the X-rays pass through the body and reach the image receptor, meaning more being transmitted, in those areas on the X-ray image, they will be darker. All right, now I'm gonna put my, where'd it go? Mouse here, but I also want you to take note of, not mouse, laser here. Hopefully you can see this, but I also want you to take note of these air gas patterns in the bowel, these darker areas in the bowel, because air is there. All right, so things like the lungs or the bowel, when there's air within the bowel, they are going to allow the X-rays to penetrate through. If they're penetrating through easily, that means that the X-rays that are exiting in that portion of the at that portion of the image receptor are going to be darker. All right, so the darker areas, like these blacker areas, basically means that a lot more of those X-ray photons were transmitted and reached the image receptor. All right, then we have all of the in-betweens, which we do need. We have all of those different shades of gray. So we started earlier on with the term differential absorption. So based on the tissue type, the different types of tissue will absorb the X-ray beam differently. Some are going to absorb more of the X-ray beam, and some are going to transmit more of the X-ray beam. the way that it interacts with the X-ray beam, or the way that it responds to the X-ray beam, is going to be responsible for all the shades of gray in between. So we have white, different shades of gray, and then we have the darker areas such as the black. So more absorption basically means that we're going to get areas on our image that are wider or brighter, and more transmission basically means that we're going to get areas on our X-ray image that are darker or blacker. So now we're moving on to the topic of radiographic quality. So you as a technologist, when you are out in the field, with each image that you take, you want to ask yourself, is it a good image? Is this image good enough for me to send on to the radiologist for the patient's diagnosis? Or do I need to repeat the image because it's, of poor quality, it's non-diagnostic? So there's two, I'll say, broad categories that we want to think about when we're asking ourselves that question about image quality. All right, the first category deals with the visibility of the structures within the image, and the next category deals with the accuracy of the image. We're looking more so at detail of the image. Now, this doesn't take away from the fact that before I even start asking myself the question, the first question needs to be, is all of the anatomy that is required for this image in there? And if all of the anatomy that is required for the image is there, then you move on to this. All right, so the first category there deals with the visibility, and there's two, I'll say, definitions per se that are in that visibility category. All right, so can we actually see the anatomy that we need to see? All right, that depends on things such as density. The new term for density is brightness, and also the contrast in the image. We need enough of a difference between the light areas on the film, the dark areas on the film, and also the gray areas on the film to clearly see the anatomy that we need to uncover for the patient's diagnosis. So visibility deals with density, aka the new term is brightness, and also contrast. All right, the second category, we're talking about how accurate that image is. So we're looking more so at sharpness. Are the structures that we're seeing in the image nice and clear and visible? They're not blurry. All right, if so, we're talking about terms such as spatial resolution and also recorded detail. All right, these are both important. The last bullet point right there under accuracy is distortion. Now, sometimes we want distortion because maybe we're trying to uncover some underlying anatomy. So maybe we will put an angle on our tube, or maybe canter or move the body part in a different way, such as going from a PA to a oblique, etc. But there are times when distortion is definitely unwanted. All right, so when we're talking about distortion itself, some terms that you need to think about are elongation, foreshortening, and also magnification. We don't want our anatomy to be stretched out more than it should, or foreshortened more than it should, nor do we want it to be a different size or shape than it actually should, unless that is what the imaging protocol calls for. Now we're specifically just talking about one of the factors in terms of image quality. We're going to talk about image brightness, also known as image density when we're talking about film screen. Image brightness is the new term that we use to describe digital imaging per se. So with digital images, typically the X-ray is going to be presented on a computer monitor. So with the computer monitor or computer screen, we're usually talking about the brightness or the luminance that's being emitted from the screen. So luminance is basically the amount of light that's coming from that computer monitor. Whereas when we use traditional film back in the day that we hung up on the light board, we use the term density because we were trying to describe how dark or how light that film was after processing. Either way, if we're using the term brightness, or if we're using the term density, we're kind of talking about the same thing. We just use the different terms based on the fact that we were talking about film screen and now we're talking about digital imaging. So the image, regardless of the term you use, has to have the right appearance in terms of how dark or how light it is. If the image is too dark or too light, it will potentially be a repeat because it has to have the right amount of brightness or density. Now, in the film screen days, density was controlled largely by mass, the mass that you set on your control panel. If you increase the mass, you increase the density. If you decrease the mass, you decrease the density. Now with digital, even though we do still have to set the appropriate mass, it has less of a factor, plays less of a role of determining the density. The reason for that is with digital, the computer system actually adjusts and controls the density more than the mass. So again, digital images, we use the term brightness. Film images, we use the term density. With digital, mass is less of a controlling factor because we have all of the internal applications and controls that we can use to, I'll say, change per se how the image looks. We can make it lighter or darker post-processing, whereas with film screen, what you see is what you get. So mass really played an important role. If the mass was too high, your image could potentially be too dark. If your mass was too low, your image could potentially be too light. All right, so now we're going to look at a visual and try to describe what we're seeing in terms of those terms that we saw in the last slide, which were brightness and density. So we're going to start off with the image on the left, all right, which is lighter than the image on the right. If we were trying to or were required to describe that in terms of density, which is overall blackness on the image, or brightness, this is how we would describe it, or this is how I would describe it if I was saying that this image is non-diagnostic. All right, if I was trying to describe it, I would say that it doesn't have enough darkness or density. All right, so insufficient density. And also it has excessive brightness. So it is too light or too bright. On the other flip side, the image on the right, trying to describe those same terms based on what you visually see, I would say that this image is too dark and it has excessive density, so too much darkness. All right, the other term, brightness, it's not bright enough, so it has insufficient brightness. All right, so in either case, these might be potentially repeats if we're talking about the film screen world. The one on the left would require us to increase the mass, where the one on the right would require us to decrease the mass, potentially cut it in half because it would be considered overexposed. Now, with digital imaging, we do have some flexibility because, again, the computer basically can adjust that brightness during what we call pre-processing, and it'll give us the best possible image that it can once it's done. And then even after that step, we can post-process the image and we can make that image lighter or darker. So again, these are just images for us to kind of work on describing how the image looks in terms of density or the term brightness. Now we're moving on to image contrast, and image contrast is basically the difference between the shades, so the lights, the darks, and the gray areas that we see on the X-ray image. And we do need to see the different shades so that we can be able to tell the difference in the types of tissues, the difference between each type of tissue. Because if everything looked exactly the same shade of gray, it would be difficult for us to see the anatomy, and it would be very difficult for the radiologist to interpret what they see on the film just because there's no differences in the shade. So The different shades happen, and we spoke about this a little bit earlier, because tissues will absorb the X-ray beam differently, that differential absorption. For example, just going back to what we talked about earlier, bone absorbs more X-rays, while air-filled organs, or air, is going to allow more of those X-rays to pass through, and that's why we see the different shades on the image. If more is passing through, that's going to create the darker, blacker shades. If more is being absorbed, that's going to create your lighter, brighter, whiter shades. So things like tissue thickness, density, and atomic number, which we talked about earlier, those are all going to affect how radiation is absorbed, and will thus play a huge part in this contrast on the image. One of the other key players in contrast, in addition to factors that affect the tissue itself, is going to be the KVP that you set on your control panel. Lower KVPs typically will give us fewer shades of gray and more of a black and white appearance on the image, while the higher KVPs are going to give us more shades of gray on the image. All right, so we really need contrast, and contrast is basically the difference between the different shades that we see on the image, and it also helps us, or allows us, or the radiologist, to be able to tell one structure from the other, or not tell, differentiate one structure from the other. This slide gives us a visual example of basically why we need contrast. So if we look at the image on the left, everything is pretty much the same shade. There's nothing for your eyes to separate or distinguish. So for this one, that means that we have very little contrast in this image. Now, in contrast, when we look at the image on the right, we can clearly see the different objects that were placed on that image receptor, because they all appear as different shades of gray, black, or white based on what they intercepted. Now, it's important for you to know why this happens. It happened because each of those objects that was on the image receptor absorbed a different amount of X-ray energy. Some absorb more radiation, while others allow the X-ray photons to actually penetrate, exit, and be transmitted to that image receptor. So this goes back to that term differential absorption, and this goes back to why we see the different shades of gray on our X-ray images. So think about body parts the same way. If we think about the different types of tissues that are in the body, bone, soft tissue, fat, and air-filled organs, they all absorb X-ray energies or X-ray photons differently. Some will absorb or attenuate more of the X-ray photons that are in the beam, and some will actually allow them to penetrate, transmit, and actually reach the image receptor. So bottom line here, if we're trying to explain this, in the first image where everything got through at the same degree, if everything was absorbed, or everything got through to the same degree, there would be very little for us to be able to distinguish there. Everything would look exactly the same on the image. Whereas on the image that is on the right, the second image, differential absorption, because there were different items placed on this image receptor, or there's different body tissues within your body that will absorb that X-ray beam differently, or transmit the X-ray beam differently, that is going to give us the contrast that's going to actually allow us to see the anatomy that we need to see. All right, now we're looking specifically at the term subject contrast. So subject contrast is basically the difference between the tissues inside the patient that we're imaging. So we already know that the body is composed of muscle, fat, soft tissue, air-filled organs, etc. And because they're different, we already learned earlier that they're going to absorb or interact with that X-ray beam differently. All right, bones are going to absorb more of our X-rays, while air-filled organs are going to allow more of the X-rays to pass through. Now, those differences, or different absorption capabilities, differential absorption that we talked about earlier, is what actually allows those tissues to show up differently on the X-ray image. If every tissue in the body absorbed the X-ray beam the exact same way or absorbed the same amount of radiation, then just like we saw on the image before, or maybe two before, then the image would look the same exact way all across. It would be the same homogeneous shade, and we wouldn't be able to distinguish one tissue or one structure from the other. Now, the KVP does play a huge role in this subject contrast. We're talking about how strong the X-ray beam is. Is it able to penetrate the different tissues that it is interacting with? Now, with regard to those differences in tissue and tissue thickness, that is what's going to create those different shades of gray on the image. So that leads us to those terms at the bottom, grayscale and also scale of contrast. So your grayscale is basically the different shades of gray that you see on that digital image. So how many shades of gray that you can see on your digital image is something that is basically dictated by the capabilities of your imaging system that you purchased. Now, there's only so many amounts or shades of gray that we can see with the human eye, but that is what that term grayscale means. All right, the next term there is scale of contrast. Well, with the scale of contrast, we're basically just talking about whether we have a lot of different shades of gray or whether we only have a few shades in that image. So if we see a lots of shades of gray, as with an abdomen image that has no contrast, so your regular abdomen image, we would call that, because it has lots of shades of gray, a long scale contrast. All right, lots of shades of gray, long scale contrast. All right, if we're looking at an image that has fewer shades of gray, so let's think about any bone image like a hand or a foot. All right, it has fewer shades of gray. We're basically somewhat just looking at black and white, where you can see the obvious differences between those black and white features. We call that short scale contrast. So basically, what this particular slide is trying to get you to understand is that the different tissues absorb the X-ray beam differently. All right, because of that, we create what we call subject contrast. All right, the number of different shades that we see in the image will determine whether or not it is short scale or long scale contrast. So now that we talked about grayscale, which we said it was basically just the number of shades of gray that we can see on the image, now we're going to talk a little bit about the scale of contrast. I want to show you what it means visually. Now, personally, I don't like the fact that we have the step wedges here. So I want you to imagine in your mind or replace the image on the left where it says short scale with just a bone image. Any bone image you can think about, knee, hand, foot, etc. And the image on the right, I want you to visualize an abdomen, no contrast. So a patient came in for an abdomen and you didn't give them any contrast. So just a basic abdomen. All right, so those are the images I want you to think about as we're going over this. All right, so this image on the left, again, I told you to think about a bone image. There's only a few shades between the black and the white. All right, this is what we would call short scale. So we learned short scale. Now we're going to attach the term high contrast. If something is considered to be short scale contrast, it's also considered to be high contrast. So the difference between the shades are very noticeable, and it looks more black and white with fewer shades of gray in between. All right. Short scale contrast typically is going to be associated with lower KVPs. So again, we commonly think about those exams where we can see the obvious differences in the structure. So we're talking about bone work here. All right, now moving on to the image on the right, we see a lot of different shades of gray. All right, so we don't see that huge drastic jump from black to white. So if we're looking at something like this, and I told you to think about an abdomen image, we call this long scale contrast. So the next term that we're going to attach to long scale contrast is also low contrast. The changes that you see from one shade to another shade is a gradual change. It's not a big jump. So think about if you only like to wear pink clothes. If you had every color in the pink spectrum, that's what we would be thinking about here. All right, long scale contrast usually is going to be associated with high KVP. All right, so a good example of it, some books like to use the chest. I like to use the abdomen because in an abdomen that has no contrast, contrast instilled meaning you've had them drink barium and you can see it, bright white on the image. I like to use that when I talk about low contrast, long scale. All right, so with that, you can see that you know where the different body parts are and the different portions of the bow are based on the fact that you know anatomy, but you can't say for sure where they sit and how they move unless we gave that person some contrast. Everything is just a blur in terms of a shade of gray, a different shade of gray. All right, so again, put this in your notes. If we're talking about short scale, we're talking about seeing few shades of gray on the image, and we also consider that to be a high contrast image, and it's usually produced by lower KVPs. The one on the right, when we're talking about long scale, we're talking about lots or many shades of gray. We also can describe it as having low contrast, and this usually happens with higher KVP. So again, this goes back to the grayscale telling you basically how many shades of gray you have, and the scale of contrast is basically going to describe those shades in terms of how the image looks. All right, if it's a black and white film, meaning a bone image, it's considered to be short scale. High contrast, if it's an abdomen, no contrast, some books again use the chest, is considered to be long scale, where we see lots of shades of gray. It's a low contrast image, and it usually happens as a result of higher KVPs. All right, so now we're moving away from how light or how dark our images are in terms of brightness, density, and contrast. Now we're focusing on how sharp or detailed the image is. All right, so some terms are thrown here at you. We have spatial resolution, and we also have recorded detail. So make sure you look at your book to define these terms. So spatial resolution is basically the ability to see small structures clear and separately within the image. For example, if you have two tiny structures sitting very close to each other, can you actually tell that there is two structures there? Can you tell them apart, or do they blur together? All right, the better spatial resolution, the more small details we can see or you can see. Now, recorded detail is somewhat similar to that. It's referring to how clearly and how sharply the edges of your anatomy that you're recording are on that image. So think about the edges of a bone. All right, if those edges are nice and crisp and we can see the details of it, or we would say we could see the details of it, versus if the edges looked a little bit fuzzy and blurry. If they're nice and crisp, we have good recorded detail. If they're fuzzy and blurry, we have poor recorded detail. Maybe you saw some of this in your lab as you were practicing with your VMC experiments. Now, no x-ray is going to be perfectly sharp. We're always going to have some degree of unsharpness. And the reason for that is because we're imaging 3D objects, right? So there's always going to be some degree of unsharpness. But our job as the tech is to ensure that we control the factors that we can as much as possible. So we want to control the factors that can cause things such as blur. So again, spatial resolution is how well we can see the small details, and recorded detail is basically how sharp and how clear those details appear on our image. Now we're moving on to distortion, and distortion is basically means that the anatomy on the x-ray doesn't look exactly like it does in real life. And there's two main types of distortion. We have size distortion, and we also have shape distortion. And I'm really glad that you were able to do that lab VMC exercise prior to getting to this chapter, because some of these things you might have noticed and reported in your experiment already. So you already know what they are. Now we're just going over them after the fact. All right, so size distortion means that the anatomy looks bigger or larger than it actually is, and we call it magnification. Magnification or size distortion is affected by SID, meaning how close the X-ray tube is to the image receptor. And then it is also controlled by the OID, meaning how far away that body part is from the image receptor or from the table or from the upright bucky. So OID, what I want you to think about with OID is, and you again already experimented with this, the farther away that part is from that image receptor, the more magnified it's going to appear. All right, that's one reason why we try to ensure to keep the body part as close to the image receptor as possible. All right, the second type of shape distortion the second type of distortion is called shape distortion. And that basically means that that anatomy is the wrong shape. It can be too long or longer than it should be. We call that elongation. Or it could appear shorter than it actually should be, and we call that foreshortening. Now, shape distortion happens when either the X-ray tube, the body part, or the image receptor are not properly aligned. So what I want you to think about really quick in terms of not properly aligned is think about when you're doing a chest X-ray. Visually, when you're doing a chest X-ray, your tube is at a 90 degrees and perpendicular to the patient, meaning it's shooting straight at the patient. The patient is flat up against the image receptor, and the image receptor is flat behind the patient. So everything is on the same line. If either of those parts are moved in an unnatural way, meaning not what the procedure called for to get that image, it will create some sort of distortion. And if I can recall or remember correctly, to look at this one last week, the distortion, we told you to put an angle on your tube. I think we said 35-degree angle, but if we were talking about in the VMC, if it was the upright bucky, we couldn't use a 35-degree caudad angle because we maxed out of the tube height. There was no way to raise the tube higher, so we decreased the tube angle somewhere between 10 and 17 or 18 degrees caudad. All right, so what you saw with that angulation on the tube, you were to compare your baseline regular chest X-ray to the second image where you gave it an angle that was intentional, but it's not supposed to be there because that's not what we are looking for. And what you should have visualized with the new chest is that it looked different from the chest that we would get for diagnostic purposes. It kind of threw some of the anatomy longer, flatter. It threw maybe the clavicles out to where they didn't need to go. So that's what we're talking about in terms of shape distortion. When you think about distortion overall, basically we're just wanting to think in our mind, does that anatomy look the correct size? And also, does it look the correct shape? If the size is wrong, it's usually going to be in terms of magnification. The part is bigger than it normally would. If the shape is wrong, it will usually be those terms elongation or foreshortening. Now, what I want you to think about in terms of when I say magnification, one of the things that we have to pay close attention to in terms of chest imaging is the heart size. So we have a 72 inch SID for the heart. We typically image left lateral, and of course the patient is flush against the board. Now, the reason why we use a 72-inch SID, that's a standard protocol, but if you went back and changed the SID, what I want you to look at, which you did already, is what happened to the heart when you brought the tube closer. Also, with left lateral, all right, the heart is typically kind of shifted to the left side. So the reason why we do the left lateral, so that we can get the heart as close to the chest bucky as we can to reduce the distance. All right, if we did a right lateral, that means we're putting more distance. We typically don't do a right lateral, but if we did do a right lateral in the field, you're putting more distance between the heart and the image receptor, and potentially that would induce a lot more magnification. Now, you want to ensure that you always use the standard SIDs, because that is what could occur. That magnification could occur in the image if you're not using those standard SIDs. Now, how can we, let's say we could not control one of those factors. Let's say we couldn't control the OID. If you could not get the patient's body part as close to the image receptor or bucky or table as possible, one way to counter that magnification is to increase the SID. But we're not talking about that at this moment. But just food for thought, a way to counter or deal with the OID, because we already know that it's going to magnify the image more than it should be, then we could increase the SID to counter that. All right, so this gives us a visual of some of the things that we were talking about in terms of distortion. Now, it doesn't give us the magnification, but it does give us what motion does or would do for an image, and also it shows us a little bit about what shape distortion is. So on the left, we have an image of a chest, a lateral chest. All right, and the caption is that there is motion and unsharpness. So you can look in your book if you can't see this clearly, or you can try and blow it up. But basically, it's showing you because there was motion, meaning the patient was probably breathing when they weren't supposed to. Breathing instructions are second inspiration for chest, and they're holding it in, they're not breathing. But as a result of them breathing, the edges of the anatomy are kind of blurred. They're not sharp. All right. So any type of motion, if a patient moves or part moves, just like in regular imaging, if you were trying to take a picture of maybe your kid or significant other or something, and it moved, just like, unless you were using, the camera setting that's looking for motion, just like it creates blur in an image, the same thing happens in an X-ray. All right, if there's any motion that's unintended, it's going to give you that unintended blur or motion artifact. All right, motion, if it is in the image, it does basically detract from that spatial resolution. We're not going to be able to see things as clearly as we need to see it. All right, the second image there, we're looking at that shape distortion. So we have an object, and the object is the same object, all right, but it looks very different. All right, it can look different based on the tube, the object or body part, and the image receptor alignment, how it was positioned. All right, if there's any move in one of those alignments, intended or not intended, you can create elongation and also foreshortening. So those are the two types of shape distortion. So shape distortion is the body part in terms of the shape is the wrong size. Motion causes blurriness. And of course, size distortion is magnification, meaning the part is larger than it normally should be. So as a tech, these are some of the things that you're going to be looking at. As you get more muscle memory, get familiar with looking at images, you'll be able to clearly identify when something doesn't look right in terms of motion, in terms of shape, and also in terms of size. Now we're coming back to the topic of scatter radiation. So if you remember earlier, we talked about Compton scatter. We said in that Compton effect that incoming X-ray photon interacts with the patient's tissue atoms. It interacts with an outer to middle shell electron. It ejects it, but it keeps some of its energy, and it changes directions. All right, when it changes direction, it just keeps on traveling. Now, the problem with this scatter radiation is that it can eventually make its way to your image receptor. All right, if it does reach your image receptor per se, it doesn't give us any additional value or any additional information if it reaches. It doesn't help create a better image. It actually makes the image worse if it reaches the image receptor. It puts what we call fog or unwanted exposure on the image receptor. So when we talked about it earlier, think about when you're driving your car. When you're driving your car and it's foggy, it's difficult for you to see. The same thing with our images. If there's a lot of fog on the film, then it makes it more difficult. It basically deters or makes the contrast of the image worse. All right, so scatter actually decreases that image contrast for us. Now, our digital systems or digital image receptors, they are very sensitive to scatter. So even small amounts of scatter can actually make those images or decrease those contrasts in those images more than it did back in the film screen days. So the reason why it's important for you as a technologist to control fog is for this, not fog, control scatter is for this very reason. If that scatter radiation, especially if it's in excess, reaches your image receptor, it can decrease that image contrast, make the image worse, and sometimes it can affect whether or not the radiologist is going to be able to read that image clearly. Now, how do you control fog? You'll learn about it a little bit later. We control fog, not control fog, control scatter. We control scatter with the collimation. All right, so we want to make sure that we're collimating to the best of our ability, and we can also control it by using a grid. Now, any Bucky work already has a grid, but when you're out doing portables, sometimes you might have to use a grid or take a grid with you. All right, so now we're going to look at an image and kind of try to see what scatter can actually do for the image. So let's pretend that this is a diagnostic T-spine that we're looking at right here. It's really difficult to see, so that's why this image is kind of good. So if you can remember, scatter radiation is radiation that has changed direction after it's interacted with the patient. Now, if that scatter radiation reaches the image receptor, we already told you that it's not going to give you any useful information. Instead, what it does is it adds this gray, foggy appearance that you kind of see right here with this quote-unquote T-spine that we said we were looking at. So think back to what we said or what we learned about contrast. Now, we do need all of these different shades or different differences between our light areas, our dark areas, and our gray areas to see all of the anatomy clearly. But when scatter adds all of this extra gray on the image, the differences that we need actually start to disappear. So that means the more scatter that is on the image, we will actually have less contrast. So the image, like the one that we see here, it starts to look flat or washed out, could be a term that you could use. And it does make it a lot harder to distinguish one structure from the other. So this is why it's important for you as the tech to control fog or control scatter. And we do that again by collimation and then also using grids when a grid is necessary for use. Now, bottom line is when we're talking about scatter, scatter creates fog, and fog, if it's present, can decrease that image contrast. All right, now we're moving on to image noise, also known as quantum noise. Back in the day, with film screen, this would have been called something called quantum model, but it all basically is created by the same thing. So quantum noise is basically that we have an image that has a grainy or speckled appearance. The biggest thing to understand about noise is that it happens when the technique is too low. So if the technique is too low, that means that not enough X-ray photons reach the image receptor. So if not enough X-ray photons reach the image receptor, you can't create the image that you need. So with that being said, it's really difficult for me to, from looking at this slide, to distinguish which one is noisy versus which one is regular. But the noisy one has basically a grainy or speckled appearance, so to speak. Now, noise, if it is present, it doesn't give you any useful information. All right, it only will interfere with basically being able to see the anatomy clearly. And of course, if we were to send this across to the radiologist, it would interfere with the diagnosis for the patient. It would actually delay it because they would probably call back and say, who sent this? Why did they send it? You probably get in trouble, and the patient needs to be called back in for a repeat. All right, with digital, the image could still look good per se, but if the speckled or grainy appearance is there in your mind, you need to know that the only way to improve that, there's no amount of what we call window and leveling you can do to improve that. The only way to improve it is to repeat it with a higher technique, because we already stated that not enough X-ray photons reach the image receptor. So we're going to repeat it with a higher technique so that more of the X-ray photons, they'll be stronger. They'll be able to interact with the patient, exit, and be able to be transmitted for for the image, to make the image per se. All right, so again, image noise is not a good thing. In your mind, if you ever see an image that you create, and maybe you saw this in your lab, I'm hoping that you did, when we were decreasing the technique, because I feel like I had some frustrated students that were concerned because when they were decreasing the techniques, the images, in their mind it should have been diagnostic, but in their mind the images, or visually the images, got worse. So the same thing applies with noise. If noise is present, you must repeat it. There's no amount of windowing or leveling that image you can do post-processing to fix it. You have to repeat it. All right, now we're moving on to image artifacts. All right, an artifact is basically there's something in your image that shouldn't be there, like a necklace, or let's say we were doing a skull series like earrings, and a chest, maybe piercings, and sometimes you can't take those out. Skull imaging, maybe bobby pins or a wig, even a pacemaker or the leads when you're doing a portable, those are even considered to be artifacts. Now, some, of course, we're not going to be able to take out or get rid of, but some we actually can. Now, in your VMC simulator, if you're ever paying attention, which you have to, you'll notice that there's a man that shows up and he kind of has a necklace on, and you have to click him off. If you don't click him off, sometimes, let's say if it was a chest image, then the patient would show up, the image would show up, and there would be a necklace in the anatomy. So you would have to go back and repeat it and take that necklace off. So again, you're responsible for ensuring that there are no artifacts in your image. Things like I said, jewelry can create an artifact. Sometimes clothing, when the patients come in and they have like words or pictures on their shirts, those can create artifacts. Zippers can create artifacts. Different types of bras, especially if they have the underwire, can create artifacts. Buttons, hair can create artifacts. One strange artifact that you might see, this is why we have patients that have really long hair. We try to have them pull it up or out of the way of the image. If hair is wet or if hair, is braided, it can create an artifact. And like I said, medical equipment such as pacemakers and the leads from um, the EKG machine, those also are considered to be artifacts if they show up on the image. Now, the reason why it's important for us to ensure that we don't have artifacts, if they can be taken off per se, is that they can cover up some of the anatomy that the doctor or radiologist needs to see. All right, so it could get in the way of some important anatomy that they need to see for interpretation of that image. So again, just like in the VMC, or even with this one, we would need to repeat this patient and we would need to tell him or her to take the necklace off. Now, we should have done that at the beginning when we got the patient dressed, but this obviously was missed on the patient, or maybe they came in as a trauma and it was missed. But in any case, this happens in real life, and the only way to get rid of this artifact, which we would want to get rid of, is to retake it with that necklace removed. All right, artifacts themselves, they can be lighter or darker than the image. So we would classify them as a plus density or a minus density artifact. All right, this one that you see right here is considered to be a minus density artifact. It is lighter than the surrounding area, meaning the necklace is lighter than the surrounding area. Some of the density is missing, is the way that I look at it or interpret it. What I would consider a plus density artifact would be something like a double exposure. It would probably be difficult for you to get a double exposure these days because we're using digital, unless it was maybe a CR image and you mix up your film and shot one body part over another body part. But the only potential way to maybe get what I would consider similar to a double exposure is when you haven't cleared a body part from the anatomy that you're imaging, meaning you're doing a hip or pelvis and the patient's hands are kind of behind his leg. That would be an example of what we would consider somewhat a double exposure, not a true double exposure, but you have two images sitting on top of each other based on the fact that you didn't clear the arms and hands from the body part that you were interested in. Now we are moving on to digital image characteristics. So when you make that exposure for your patient, the image receptor or detector receives some X-ray information that's going to create what we call a latent image. All right, a latent image is basically an invisible image until that data is processed and gives us the image that we see on the actual computer monitor. All right, the one that we see on the computer monitor is called the manifest image. All right, so latent again just means that the image is there, but we can't see it yet. Just like a latent disease means the disease is there, but we haven't seen the effects of the disease yet because it's not like fully engaged with the body yet. All right, now once our image is processed, all right, once the image is processed or once the computer processes it, eventually it's going to show up on our computer monitor as the manifest image. All right, so what we see from that processed image is made up of what we call pixels. All right, pixels are tiny squares. All right, pixels are also, another word for pixels is also picture element. So think about when you're taking a picture with your phone and you're zooming in or out really far, eventually you'll start seeing tiny squares or tiny pixels or tiny squares or pixels. Sometimes also when we send images, or receive images and we look at the image and the image quality is degraded, we can sometimes see the individual pixels. When you're also buying a camera or your newest phone, some of us are sometimes interested in the MP of the camera or the megapixels that it has, because we already know, well, we don't know, but and don't think about it in this way, but the more pixels or megapixels that the camera has, the better quality those pictures are. The same thing happens in X-ray. We're talking about digital images as well, but we're just talking about X-rays. All right, now once those pictures are processed, the pixels will make a difference, or the number of pixels that we have will make a difference in what we actually see in terms of quality. Now, the pixels are arranged or organized in what we call a matrix. All right, so a matrix is basically a grid made up of rows and columns. So think about, if you play checkers, think about a checkerboard. All right, the checkerboard has all the squares. Each individual square on the checkerboard, we would call that a pixel. All right, the matrix and the pixel can determine what the image actually looks like. All right, when the image is actually being processed, meaning you shot the patient, the matrix received all of those X-ray energies in the different pixels. All right, each pixel now contains a numerical value based on how much X-ray was detected in that particular area of the image receptor. Now, the computer itself will take those numbers and it will turn those numbers or values into different shades of gray so that we can see that final finished image. All right, so what I do want you to take away from this is pixels. In terms of pixels, the smaller the pixels are, typically the more pixels you can fit in the matrix. And if you have more pixels in the matrix, then your image will probably be of higher quality, meaning it can have more detail. So that's why it's real. Knowing what pixels are and what they do for us is really important. But these are really definitions that you need to know: matrix, pixel, latent image, manifest image, and then also know how pixels can affect your image quality as well. Okay, so on the last slide, we talked a little bit about pixels and we also talked about the matrix. All right, the pixels fit in the matrix. So on the last slide, I think we said to think about the matrix as like a checkerboard, and each square on the checkerboard is a pixel. So the more squares that we have on the checkerboard, the smaller the squares will be, and therefore the smaller the pixels will be. And smaller pixels allow for the image to have a lot more detail. So the images at the bottom are basically trying to get you to see how as the matrix gets larger, the image actually gets better. There's more detail. And when we say matrix gets larger, we're not saying that the image receptor per se gets larger. We're saying that there's more rows and columns of squares and smaller squares than the smaller matrix. So if you were to blow these up, on the smaller matrix, you would be able to see some of the squares, such as on cameras that don't perform really well. You might be able to even see the individual squares within the pixel. As the matrix gets larger and those pixels get smaller and closer together, it gives us better detail, and of course, we're not able to see the individual squares of the image. One thing that I forgot to mention on that last slide was the downside to having images with a lot of pixels. All right, so the more pixels you have, that means that that's more information that that image actually has. The more information that the images have, the more storage space is required in whatever system you have. So for us, we're talking about our PAC system. So we're talking about larger files based on the fact that those images contain all of that information. Now in telemedicine, if I was trying to send these images from one location to another location, one hospital to another hospital, that means that the transmission time as these files get larger and larger can be slowed down as a result of the information it needs to send. Just like when you send files too, some files transfer really quickly and they get to the person really quick, and then some files, based on how much information you had in the email, may take a little bit longer to get to the person because of the transmission speed. All right, so now we're moving on to pixel depth. We already know that pixels are those tiny squares that make up the image. We know that the pixels fit inside that matrix or sit or make up the matrix. But for you, what you need to know is that each of those pixels, after the image receptor receives that radiation, will eventually be assigned a shade of gray. Some pixels might be very dark in terms of the image, and some of those pixels might be very light, and some might fall into the different shades of gray that we see in the image. Pixel depth and also bit depth basically tells us how many different shades of gray that system is going to be able to create on that image. All right, so that formula that you see right there, 2 to the power of n, all right, that n is simply the number of bits that the image has. So for instance, like a 4-bit image. So I would take the fact that it was a 4-bit, I would replace the n with 4. 2 to the 4th power is, if you do your calculations really quick, it comes out to 16. All right, so it's not 2 times 4, which is 8. It's 2 times 2 times 2 times 2. I think I did four twos, and that comes up with 16. So that means that that 4-bit image can have 16 different shades of gray in it. All right, another example, let's say we have an 8-bit image, or a machine that was capable of 8 bits. All right, so we would replace the n with 8, 2 to the 8. If you take a moment to calculate it, you can do it simply, or you can just use your smart calculator. That should come up to 256. So we're talking about 256 possible shades of gray. All right, one more example, if we have a 12-bit system or 12-bit image, all right, 2 to the 12th power. All right, if you calculate that up, there are going to be 4,096 shades of gray available for the assignment of those different pixels in the matrix. So an easy way to think about it is, so let's say when you were a kid, some of us got the little box of 4 to 8 crayons to 16 crayons, and some of us got the more expensive box that had, I don't know, a whole lot of crayons. Let's say 200 crayons or more. All right, so that basically means when they colored, they had all of those different shades and colors available to make their picture, whereas us, on the other hand, with the 4 and 8 colors, we only had a little bit of shades that we can put in our picture. So that's kind of the concept you need to think about when we're talking about this pixel depth and bit depth. So with that being said, the more bits that are available, the more possible shades of gray are available for assignment to these pixels. All right, so now we're moving on to another term that you'll see in digital imaging, and that term is pixel pitch. By definition, is basically the distance from the center of one pixel to the center of the next pixel. So I do want you to think back to the matrix, or you can see this matrix right here. If we have the same size image, but we put or pack a lot more pixels into that image, that means that those pixels have to get a lot smaller, and that also means that those pixels get closer together. When those pixels are smaller and closer together, they will allow us to see smaller details more clearly. So we're talking about an improvement in the spatial resolution or detail in the image. All right, so the big takeaway here, outside of um, getting these terms in your memory bank, is the more pixels that we have, the smaller those pixels become or have to be, the smaller the pitch or the distance between the pixels, and then also the better the spatial resolution. All right, another term right there is pixel density. So when I think about pixel density, I think back to high school when we talked about population density. So pixel density just means we have a greater number of pixels per unit area or in that area. Same thing with population density. We're talking about the number of people that are in a specific area. So that's another term that you need to put in your belt or be able to understand what it is. All right, this next slide that is in this chapter, or the information that is in this chapter, I'm going to skip. And the reason why I'm going to skip it is because the chances of you seeing film screen out in the real world is probably slim to none. You might still see CR applications, but that's even going by the wayside. But since this is no longer on the registry, I'm not even going to focus on film screen characteristics because it's not going to be something that's important to you. All right, but I am going to focus on dynamic range, and I'll reflect back on film screen just to give you an example of what dynamic range is in terms of the difference between then in the film screen world and now in digital imaging. So dynamic range is basically how much exposure the image receptor can handle and still be able to give you that diagnostic image. Digital X-ray has what we consider a wide dynamic range. So it can handle really large exposure differences, like really small exposures or low exposures, and it can also handle really high exposures and still produce a good image. Digital also allows you to adjust things like brightness and contrast post-processing, meaning after you take the image, same as when we do images of our selfies or our kids, we can change those images after the fact. We can do that in imaging. I mean, in digital imaging or in X-ray imaging. With film screen, what you see is what you got. So we said that film screen world, we had a narrow range. The range was narrow, meaning you either had a good film, you either had a bad film. All right, an overexposure or underexposure was a bad film. Overexposure, underexposure is definitely a repeat. In your world now, digital world, if it's overexposed, meaning you use too much technique, as long as it wasn't gross, the digital system or computer system might be able to fix it for you, and you still may be able to do more post-processing. If it's underexposed, as long as it wasn't gross and your image was not noisy, meaning grainy, then you can still be able to fix it post-processing, and your computer would try to fix it before it got to you, but you could still do some changes via window level post-processing. All right, we did not have that ability in the film screen world. All right, what you see is what you get. So if I was shooting a foot and I use a toe technique for the foot, if I was interested in the tarsal bones, then they would be too light. Vice versa, if I was shooting a foot, but I was really interested in the toes and I used a foot technique, then the toes would be burned out and it would be a repeat. So it had a very narrow range in terms of film screen, whereas now with digital, you have a large or wide dynamic range. You can handle a lot more of the differences, and you can also post process the image after you see it on the screen. All right, so again, wide dynamic ranges basically means there's more exposure levels that the image receptor can handle, and it can handle it and still give you a good image or diagnostic image, even though Jane's technique for the same thing is different from John's technique for the same procedure, but they both still get a good image. This is something that you'll see when you do get out to your clinical setting. When you're working with techs, you'll notice that some change technique, some dial it in, meaning they select the body part and they use whatever pops up, or they use the AEC, and some you'll notice that whenever they start imaging, they change their KVP or mass. Now, when you see them change their KVP or mass when you're out in the real world, what I do want you to do is note those changes in your mind or in your little notebook. Hopefully you have a notebook, or hopefully you've purchased the little pocket Bontrager or Merrill's, whichever one you prefer. I would say, well, I guess it really doesn't matter because you're going to clinic at the end of your term. So if you purchase one of the handbooks that you can put in your pocket and take to clinic, it basically gives you the majority of the procedures. It gives you how to position, CR angle, etc. There's a place for you to put technique and other notes there, and it gives you pictures of what you should see. So you're not carrying around, you don't have a book, but you wouldn't be carrying around your big Bontrager or Merrill's versions like the brick and mortar students. Now with this, when you see your tech changing those numbers, you do want to pay attention and you do want to mark them down. All right. Once the patient is gone and there's some downtime, do take the opportunity to ask your technologists why they made that. Now, hopefully you saw this in your experiment when you were changing your MA, your S, and your SID, OID, etc. Hopefully you paid attention to that lab carefully so that you noted what happened when the MA went up or down, when the time went up or down, or when the KVP went up or down. But if you don't recall or remember or didn't really pay attention to the lab, when you do get to your clinical setting, as you know, patients come in and out and there's downtime, go back to your tech and ask the question, you know, hey, do you remember when we did this patient? Why did you change the numbers? Why did you change the mass? Why did you go up in the mass and didn't leave it where it was? Why did you go down in the KVP or go up in the KVP? All right, if you really want to understand technique, because a lot of students, especially the new students, and especially since we're not in the film screen world, when you had to know technique, since everything is so automated, it takes or will take a conscious effort for you to learn technique. And the reason why you want to know technique and what happens when, you know, the technique is too low or too high and how to adjust it is because if any of those automated features of your system stop working, and you don't know how to adjust them manually, then you're basically in the dark. You're basically a sitting duck. So you really want to understand what those changes are. And if you get an image that is considered to be a repeat, or you need to repeat it, and you're not at a place that has all of this automation, what do you need to do in terms of technique adjustment to get a better image on the repeat? Because we're not just here repeating in the dark. There has to be a rhyme or reason why we're repeating, and there has to be specific things that are done to the technique in order to get a better image the next time. It's just not a matter of bumping the mass up to and the KVP up to. There's a specific amount that needs to happen, either double the mass or cut the mass in half. KVP, we function on the 15% rule, so you're either going to increase it by 15% or you're going to decrease it by 15%.